So, we talk about math a lot, and now I want to talk about FPGA processing and how it can help you to build software that runs really fast on embedded systems. So, the FPGA is an acronym for a Field Programmable Gate Device. Basically, it's a chip on a hardware that contains a lot of logical elements that you can combine in any fashion as you wish to achieve a function as your problem is. This small device is quite powerful, and it can guarantee a speed up at 10 or 100 or even 1,000 times faster than regular CPU can provide with the same problem. It can help you if you, for instance, running low on a CPU speed, for instance, for real-time data processing or in networking. The use of FPGAs are very common because they help to process UDP packets very fast. Or if you don't have enough power to, for instance, power up the Core i5 processor. So instead of spending 100 watts on solving one task on the CPU, you can spend 2 watts on solving the same task on FPGA, and it will be faster. But programming for FPGA is a quite complicated part. So you should start from having the general implementation of your algorithm. It should be correct, right? So, yeah. Then we usually apply some kind of multi-threading using threading blocks or OpenMP, whatever, and we employ vectorization of our CPU. If that's not enough, then we start do cache tuning to optimize for particular processor and employ OpenCL, for instance, to employ our GPU. Yeah. But what if that all steps are not enough? So in this case, we can use FPGA to put our work into hardware, because hardware is obviously faster than software implementation. So, and FPGA does it by having those building blocks that contains the logical cells, the memory, the lookup tables that help us to build a function of any kind that we want to. So the LUT is a lookup table. It's actually a logical unit that does bit operations. It can invert bits, do AND, OR, and any other logical functions. The flip-flop, they are the most closer alternative in the regular processor is a register. So flip-flop just holds the intermediate results of the lookup tables. Also, there are arithmetical logical units that can compute arithmetical operations like a sum or subtraction, multiplication, but they can be combined to build more complicated functions, and they operate really fast. I will show later how fast they are. And of course, there is a called blocked RAM. It is not the same RAM as we have in our laptops. This is much faster. This contains no restrictions on cache misses, and it serves as an intermediate buffer between our FPGA and the user code. And of course, to communicate with the periphery, there are input-output ports that are wiring the rest to get it working. I mentioned that FPGA programming is hard. Yes, it is. Historically, FPGA had been using for decades because they provide the performance that is not compared to the regular CPU. So here are CPU implementation, and there are FPGA. But as you can see, in terms of the performance and time, how far FPGA on this chart is. So this is because FPGA programming has nothing common with C++. With FPGA, you program how register transfers performance in the chip. So you have to keep in mind a lot of variables, a lot of spatial and time information, because with the FPGA, you have to keep in mind when the data begins to arrive to your chip, when it becomes available to the next step of processing, when it becomes ready to be right back. And this is really hard, and that's why FPGA programming is usually not so popular as another optimization techniques. However, FPGA is much faster, and here's why. The generic CPU executes any program with a sequential order, and each instruction usually split by a few phases, which instruction fetch, data fetch, execution, memory operations, and write back. Modern CPUs have much more fine-grained stages. So, for instance, Core i5 have 16 or 18 phases per single instruction. This is done intentionally to employ pipelining. So modern processors have several execution units that allow us to execute our code in a kind of parallel way. So while the first instruction gets executed, the CPU can start running another one instruction. So here in this example, we have probably 5 execution blocks that allows to instructions to run in a parallel. So in each cycle, we execute exactly only one instruction. This technique allows to write faster code on a CPU, and all compilers that exist today know about this feature, and they try to arrange generated code to employ this technique. Unlike the CPU, the FPGA has no this restriction. They can execute instructions in a parallel at the same cycle. And here are 5, but we can have 1,000 of the same instructions running in parallel on FPGA on the same cycle. Here, and obviously, if we run 1,000 instructions, we'll get 1,000 speed up. For recent, few years ago, the Vivado, it's an application built by Xilinx. Xilinx is a vendor of FPGA chips. Did a nice thing. They built a tool that allows us to convert our C code, C or C++ code, into FPGA design. So basically, we take our program definition in C++, our implementation of algorithm that is too slow for a CPU to achieve real-time performance, for instance, and we put it into FPGA, which also gives us the same performance as we do achieve with manual coding, but it saves our time. And on this chart is a diagram that shows that time efforts required to achieve the same performance are much lower. And by having this tool, we can translate our existing code into FPGA and get it much faster, because it fully supports C++ 11, and it allows you to reuse your code. You don't have to invest a lot into training some guys that are aware of integrated circuit or semiconductors, and you can just translate your code into FPGA logic and get a result. So HLS compiler, this is a high-level synthesis. So they call this technique a synthesis because they synthesize a design for a FPGA chip. It does a lot of job to optimize your code to target FPGA device, and it also allows you to do very interesting thing. With a general CPU, we usually have ints, floats, yeah, or doubles with a 64 bits depth. But if we don't need, for instance, 64 bits, but 32 is not enough, we can do nothing with it. Yeah, with FPGA we can do mathematical operations on arbitrary precision types. For instance, we can have 9 bits digit. That's fine. Or 70 bits float. That's also fine. And that also will work for sure. And as I said, the high-level synthesis optimizes implementation for a particular chip. This is very important since each chip has its own capabilities, like a number of arithmetical logical units or number of memory on its frequency, operating frequency. So when we design, we usually know which FPGA we are going to use. And we optimize for this particular device. And the good thing about synthesizing is it allows us to forget about pretty nasty things in a generic programming, like conditions. So when a processor does any branching, it has to predict which branch we will use. And if the compiler or if the CPU predicts the wrong route, the CPU execution engine would stall and will have to fetch the instructions for the branch it should use. This will lead to performance degradation. Unlike in CPU, the FPGA synthesizes both paths in the hardware and executes them simultaneously. And when the FPGA knows the condition result, it simply takes one or another answer and returns it to the caller. So this allows us to forget for any penalties for loops, because all loops get synthesized, gets called, and you get a right result. But since FPGA is a parallel device, there is no penalty for branching. But there is also no such thing as dynamic memory allocations at all. So you cannot use STD vector. You cannot use new operator. You can not allow it to delete or allocate memory. You can just end up with a static memory. That's all. This is because HLS doesn't know how much memory are you going to allocate. And that's why it cannot synthesize the particular design in a hardware to contain, for instance, a dynamic buffer. Obviously, it needs you to change your algorithms to contain only statical memory. But instead, you get the maximum performance from this memory as it's possible. Because the way you access this data depends on what will be synthesized. For instance, this buffer A can be synthesized as a shift registers, or it can be synthesized as a registers itself, or a block RAM. It all depends on how you access it. And with the HLS, it automatically analyzes the data access patterns and chooses the best way to synthesize this array. Of course, you have pragmas to control the synthesizing process. And the second thing is very interesting. The block RAM in a FPGA is very fast. So how fast is it? It provides 23 terabits per second bandwidth. Think of it. Usually, FPGA is designed to process data with a sequential order, where we have a producer and a consumer. So the data flows to FPGA from a camera sensor or from inertial measurement unit or any other data source, and we process them sequentially by blocks. And this is the way it's supposed to be used. By the way, I will share my presentation, so just in case. And the data flow requires you to know the details of how FPGA works to write code that is as efficient as maximum. So the intermediate registers store the data, the result of the evaluation at each A, B, C, D, E blocks. So like in the GPU, in CPU, sorry, when we start processing, we put data into register. On the next cycle, we compute right to the next. But for instance, if we are now in a block C, the FPGA can still use B, A, and those two intermediate registers to process data in the same way as CPU does with the pipelining. So this pipelining is super important for FPGA because it allows us to reduce the latency of the operation. The operation of latency is the time between the data got into FPGA and we got the result out. So with this pipelining technique, we receive data at a rate of 1 cycle per bit. I'm going to show you some demonstration on how to optimize existing C++ code to FPGA, but let's quickly recap what I've just taught. So no branching penalty and no cache penalty. So which means when we have the data in our FPGA, there is no cost to access it. It's a random access memory with no associated. The block RAM is an instances, the pipelining and task-centric approach. And the task-centric approach is a way how you should call your FPGA. So it makes no sense to call, for instance, a single small function like, I don't know, logarithm on FPGA. It's a too small amount, too small piece of work. Instead, you should put a more complicated, more time-consuming task on FPGA, like a whole image processing. That's the right piece of work for FPGAs. And usually when we do such HLS compiling, we start with a baseline version. We have also a simulation test that actually a test that verifies correctness of our implementation and implementation that we will end up with a HLS. Then we do synthesis, simulation, which runs the simulated FPGA on a CPU. This is usually 10,000 times slower than on a real device, but it validates that all requirements, all timing checks, all registers access it in the right order. And if everything goes wrong, you will get information about it. So then we measure how fast we are, optimize if something goes wrong, and run the simulation to verify it. On this example, I want to show you the simple optimization scenario of the Sobel operator. This is a 2D convolution of the trivial kernel. I'm pretty sure you're all familiar with it. And I have an FPGA over the frequency 150 megahertz. That's not much. The modern CPUs has a frequency of 2 or 3 gigahertz, right? But at the same time, this small guy will be able to achieve a performance of processing full HD video at a rate of 60 hertz. So just to remember, so with the Sobel detection, we convolve each pixel with a 3x3 window with to compute horizontal and vertical derivatives. And then we compute their absolute sum to get the edge for the corresponding pixel. So this slide contains the implementation of this in a C, the straightforward 3x3 convolution. And if we take this code and put into our FPGA synthesis to measure its performance, we will get all 40 cycles to process a single pixels. That is too slow, because to reach full HD in real time, we have to process data at a rate of 1 pixels per cycle. So this implementation, the straightforward implementation, is 40 times slower. So here is why. It's slower because the compiler, the HLS compiler, does not unroll any loops. So it requires some guidance from the developer to annotate this code somehow, to let it know that, okay, it's safe to unroll this loop, so he can synthesize more hardware. Why does not HLS compiler does it by default? Well, because he doesn't have information on how many hardware capabilities of our chip it can use. For instance, we have something like 64 kilobytes of block RAM and, for instance, 1,000 of the logical units. So compiler tries to use as less as it can logical blocks, but we can force it to use more to get speed up. So the idea is to pipeline the one field computation with our code. So here's a small pragma instruction, like OpenMP, but for HLS. So it tells us that these 3 lines of code, this scope, should be pipelined. The pipelining allows us to process data faster. So if we rerun simulation, we'll get 10 cycles to process 1 pixel. Okay, this became 4 times faster. It's okay, but we'll have to go on. What's wrong with that code? We unroll only the inner loop, which is not enough to achieve the required 1 cycle per pixel. So we can pipeline the whole inner loop where we iterate over columns. So the HLS pipeline pragma moved here. So the compiler will unroll those 3x3 iteration, and it will do all this in a pipelined fashion, which should help us, right? Still something not good. We get from the simulation, we get a right timing, that 1 cycle per pixel. But since we unrolled our loop, we have a 9 memory access that happens at the same cycle. This is not allowed on FPGAs, so we have something to do with the memory access violation. So it's easy to see that this task has been already solved on a CPU. Usually we solve this by introducing a temporary buffer of 2 lines, which contains intermediate results. So while we fetch data, we keep those black regions in our block RAM, so it's free to access them. So that's why we avoid 9 memory accesses. So we read 1 pixels from our input stream, put it our buffer, and from this buffer we fetch all 9 blocks instance with a 0 cost, and that's why we access only 1 element per cycle, and that's why here's how we can achieve our 1 cycle per pixel processing data rate. A common CPU would require something like maybe 100 cycles to process the same data. And the FPGA is much slower, consumes much less energy, and with putting this task to FPGA, you can free your CPU to do some other tasks. Probably you've been listening and wondering, where is the catch? Things are not so good because the learning curve for FPGA is very steep. Honestly, I spent a month to get some working results on a hardware from scratch. I think that's a lot, yeah. And the main problem is that FPGA community are not so solid. You won't find a lot of information on Stack Overflow. Instead, you have to dig into microelectronic forums and read a lot of information that is not on the first page of the Google. Yeah, and the second thing is tools for this high-level synthesis. They're quite, outdated, I would say. So yeah, they're working, they does their job, but looking at the Vivado IDE and comparing to C-Line or Visual Studio, they're just looking weird. However, you don't have to deal with them on a daily basis. Ideally, you take some code that require optimization, do HLS synthesis to obtain a bit stream. A bit stream is actually a firmware for FPGA. You upload this bit stream to FPGA and it gets ready to work. It's not a one-time operation. I mean, you can change this firmware on the fly or with a new version of your program, and it will work. The second problem that it works in a simulator. As I said, with the memory access, the HLS doesn't know that your hardware can be limited to some memory access. So that's why you can encounter a situation where whether your design works in a simulator, but it doesn't work on the hardware. And it's really hard to debug. But essentially, Vivado and Altera does a lot to make it more popular, because they provide, for instance, OpenCV port for FPGA. So this means they made some wrappers which allows you to use the familiar syntax from OpenCV to compute derivatives, do Fourier transform, detect lines, whatever, on the FPGA. So you just write regular C code that executed on the FPGA. And I think this is super cool. Also, they support OpenCL. So they synthesize code from OpenCL kernels into FPGA. That's also awesome because it allows OpenCL developers to put their code base on the new device to keep their knowledge demanded. Yeah. And I want to inspire you to try FPGA development, or maybe you will have some chance to work with it, with FPGA development boards, because I found it really exciting to work with a hardware processor like FPGA and speed up things a lot. Honestly, that's all. I want to share some results from FPGA development I recently achieved. So I've been building a software from one of my customers, and we have a really low-end processing device. It was something like a dual-core ARM chip with a 600 megahertz, with maybe 25 kilobytes of the cache, and it wasn't able to process data as a laptop device. And for a 2D tracking, we were using Harris corners that on this chip was running on 40 milliseconds, probably. That's something like that. So, but our goal was to reach real-time performance. And we put this whole implementation of Harris features to FPGA. And the way we designed our system was that camera delivered frames directly to FPGA, and we were accessing already processed data in our CPU code from the FPGA. So in this scenario, we reduced the processing time of Harris features to 0, because all the data inputs to FPGA, all processing done on FPGA with a rate of 1 cycle per pixel, and we output Harris corners directly with in our CPU code. So this processing on FPGA cost nothing for us, for the user code. Instead of 40 milliseconds on the 2 cores of the CPU. Thanks for listening.
Yeah, and we have 20 minutes for questions, so be ready.
Oh, cool. Yes, please.
Yeah.
Yeah, thank you. So you talked about your planar tracking and the high-risk corners. And the question is, so in really speaking, how much of the overall system could be potentially optimized using FPGA? So for example, 2D tracking or 3D tracking, SLAM. So you understand, yeah?
Okay, yeah.
The overall performance gain.
So the good candidates for FPGA processing are, I would say, all dense image processing routines. So this gradient computation, template matching, even key points extraction or orientation assignment is good for FPGA. FPGA good for matrix operation as well. For instance, the Kerr decomposition or matrix multiplication, the general matrix multiplication, can be easily ported to FPGA. Even with with the dynamic sized matrices, it can also be ported to FPGA because when working with FPGA, you have to hard code the size of your matrices, right? So you cannot just pass dynamic sizes of matrices you want to multiply. Instead, we can split our matrix by blocks and multiply them in parallel. That would be much faster than doing this on the CPU.
I know if it's not a secret, so for example, the planar tracking you were talking about, so you said you reduced 40 milliseconds to 0 milliseconds. So in the terms of the whole system, so for example, before optimization, the whole system works 10 FPS. After optimization, it worked 20 FPS. So can you tell the overall increase of performance?
So on Mac, the Mac Pro, the overall 2D tracker was taking 2 milliseconds. On iPhone 5S, it was 7 milliseconds. With only a single core and neon optimization for math. On target device, the whole routine was about maybe 50 milliseconds, and high-risk corners was the slowest part. The slowest part because of the small cache size of the target CPU, because the image we processed was 1080 by 720, and the cache was not enough to process data at the desired rate.
Hello, thank you for your presentation. There's an upcoming market in products containing a GPU at the moment. For example, you can find them in mobile phones and the NVIDIA board Tegra, maybe you know it. You can find it in drones. How do you see the future of FPGAs when there is loads of products with GPU on it?
As you know, most modern mobile chips are system-on-chip devices, which means they contain on the same crystal a CPU, a RAM, a DSP, and other peripheral devices. And the way of evolving of FPGAs, they are moving to the same system-on-chip solutions. So our target devices was also system-on-chip shipped by Xilinx, and so it was a FPGA with a CPU on the same chip with a memory together. And I feel that this is the way where FPGA vendors are moving to. But historically, the FPGA chips was done by Altera and Xilinx vendors, which is not very common in mobile phones, for instance. Yeah, there are Qualcomm or Texas Instruments, and the way they absent in mobile phones is they are too complicated. I would say for mobile developers. Okay. But since they are planning to support C++ with the HLS and OpenCL, it would be easier, and I think they will become more popular.
So from your experience, how much effort do you need to apply after this Vivado code translator or optimizator? So
Well. Oh yeah. In terms of developer efforts, with the HLS synthesis, it's become much less than before. But again, I myself spent 1 month to get familiar with the tooling, read papers, and get working implementation. But now, yeah, I can do this much faster. So in terms of efforts, I would say, yeah, it's quite complicated to start. It's a very steep learning curve.
Just a refinement of the question. What are the specific, I don't know, things you have to fine-tune manually after the Vivado?
Oh, okay, thanks. The annotation of your function. You have to annotate on what loops you want to be unrolled. What is the pipelining should be applied, and also you probably have to change your algorithms to conform FPGA processing methodology. I mean, it's using data streams concept that you have to apply somehow in your code. So there are classes like a data stream or arbitrary precision type that you can use to instruct the compiler that this code should be synthesized on how you want it to. So, yeah.
One more question. I have spent the time to parallelize my routines using CUDA and the GPU. Yes. Main thing, the worst thing was creating of new algorithm which allows SIMD processors, thousands of SIMD processors on GPU, to make calculation. And main idea were data processing parallelization. Parallelizator. Is data processing parallelization is main idea on FPGA? Yes.
I would say that main idea of FPGA programming is slightly different. When you have a generic CPU, the goal of C compiler is to fit your program into CPU to employ its capabilities at his best. Just finish my idea. With FPGA, the compiler takes your problem and it synthesizes a hardware design that solves this problem at his best.
Can we compare your sequencing, not sequencing, your slide when...
with the pipelining?
Pipelining, yes. No. Can you compare your pipelining with with GPU, maybe parallelizing of on the CIMD?
Yes, we can compare it with the CMD. We have how much we can have parallel computing with the CIMD? Maybe 16 elements. Yes.
No. GPU have 1,000 and more small processors, which works like SIMD. They do one operation and at one moment.
Yes.
So,
but you have to upload the data to the video memory, then compute it, and then get it back, which is done by a device driver, right? Which also takes time to CPU to process this data. Yes, with FPGA, this is all done on a FPGA controller, which is much faster.
I guess the main difference between CPU computations and FPGA computations is that, for example, in C++ you can pass pointers to some functions and you have much of context with those pointers. I mean, it's a simple operation and it comes with a lot of memory in the background. But with FPGA, you can't have much context. I mean, there is memory restrictions, and good candidates for optimizations for FPGA optimizations are operations that don't require much context. Am I right on that?
You are partially right, and that's true. You cannot store a lot on the FPGA itself. It simply doesn't have enough block RAM to contain this context. I mean, typical FPGA chip can have something like 200 kilobytes of the block RAM. So that's not much. But as a developer, you should design your function in such a way that it can be computed sequentially on the FPGA. As I showed in Sobel, we created a temporary block RAM buffer to contain 2 lines of our image to avoid memory restrictions. And ideally, all your functions should be designed the same way, so they can process data sequentially and require no big amount of context to be efficient on the FPGA. So this is what you will have to do to get the fast implementation on FPGA from your user code. But technically, FPGA can run any on any code that common CPU does. So it's a fully von Neumann processor.
I have had a small experience of the development for Altera FPGA. I'm sorry. And when we talk about FPGA, we always mean that integer digits, or maybe fixed point optimization. For example, there are many computations such vectorial mathematics, coordinate transformation, and so on, where the mantissa of the digit is very important for calculations. For example, triangle functions, and so on. How do you think? To what extent FPGA is convenient for such computations, for such kind of computations?
Yes.
Is it main constraint of the FPGA, for example, for scientific computations at all?
So FPGA are not limited to only integer computations. It can do floating points as well. And with the help of arbitrary precision data types, you can synthesize code to operate on 256-bit floating point number, for instance.
What price is this?
The price is a utilization of the FPGA resources. So, for instance, if you have thousands of logic blocks and you just require more those blocks to synthesize this function on the FPGA. So, I mean, with a generic CPU, you pay for your algorithm with the time, right? With the FPGA, you pay for this algorithm by resource utilization of the chip. So you cannot take or utilize more than you have arithmetic logical units, right? But modern chips has enough to do complicated maths, and they process UDP packets, they mine bitcoins, they can do image processing, music encoding, any other complicated things that require great performance and numerical precision as well. Yes, please.
I want to ask, is there any ways to estimate what performance boost you will get from moving your particular code, your project, to FPGA? Or you have to try to build the system and train it in hardware?
No, you don't have to build the system from hardware. You have a simulator where you put your code, it gets simulated, and at output you receive the exact timings each operation takes in terms of cycles. Yeah, so you probably can see, so they estimate that your function takes 5 cycles, for instance, and your chip running on a 100 megahertz. So by multiplying one and another, you get number in milliseconds or nanoseconds. And this is not an estimated result. This is a really final answer that this code will run on the hardware.
I will give you.
Okay, so when we are talking about FPGAs, then, for example, if I would like to use FPGA, then I would need to buy a board for this. And for example, can you give some numbers about pricing for your task when you describe this corner detection? How much would it cost in terms of board and the chip?
The development board for FPGA starts from $100, and they vary from the chip that they are built on. So it starts from $100, $115, $200 per development board. It also contains FPGA chip and all periphery you need to build and test your software. And there is IDE tools that come with it. And as far as I know, they are free, or at least partially free, because there are some things like, for instance, Xilinx built some kind of the repository of the blocks for FPGA. So these are already synthesized blocks that does some task, and they're trying to sell them to you. So this is where they take money. But the development board price is between $100 and $200. Of course, there are much more expensive development boards with really powerful chips, but for start, you don't need them. Yes?
And you also mentioned that you took the image and transfer directly to the FPGA. So the question is, what is the typical interfaces, connection interfaces?
Okay, got it. So on a development board, this is a PCI Express. In our case, we end up with a custom-made hardware design that we know that we will be running low on our CPU. So we intentionally put FPGA on our platform. So this was our premature optimization, because we are expecting this to happen.
We have here more questions. Yeah.
Okay.
Thank you for the presentation. I have another question about price. I mean, price of development. Wouldn't it be cheaper to use separate CPUs?
Well, let's calculate. If you have more CPUs, you have to change your code to support this multi-threading.
Of course.
Yes, heavy multi-threading. And but how could heavy multi-threading help you with, for instance, Sobel? Yeah, you just end up with each CPU does a very small
for example,
piece of work, and the synchronization time to get results from all these CPUs will become pretty noticeable. And also, you have to pay for increased power consumption, right?
Yeah, but I can turn off CPUs when I don't need it.
So usually FPGA are using in a field where you are limited on, for instance, power consumption or a weight of your system. For instance, if it's a quadcopter, how would you imagine a quadcopter with 4 CPUs, right?
Well, easily.
Yeah, I mean,
comparing to motors.
I mean, it's a heavy. It draws a lot of power from the battery, and your flying time reduces from half an hour to 5 minutes.
Well, okay.
Yeah, so in this case, FPGA are the best solution.
Modern DSP processor has vector computational units and powerful libraries with special C functions, which make a lot of job. And as I understood, in the case of FPGA, we should code these functions from scratch. Yes?
We code our own implementations or our own algorithms depending on our problem, right?
Yes.
Yes. What if our DSP doesn't have the required function that we need?
Okay, thank you.
More questions? No? Okay. Thank you very much, Eugene, for your presentation.
Thanks.